Hello everyone, welcome to my channel Chemical Engineering Knowledge. In this lecture we will discuss about the optimum reflux ratio. We will discuss the optimum reflux ratio, the reflux ratio and the minimum reflux ratio. So the optimum reflux ratio is denoted by R UPT. This reflux ratio is denoted by R and the minimum reflux ratio is by the. First of all, the reflux ratio in distillation column is nothing but it is the L by D. The L by D. This is the distillation column. Suppose this is the condenser. This is the L and this is the D. So this is the L, this is the D. So L by D ratio is nothing but this is speed. So this is the reflux ratio. Now this graph shows the optimum reflux ratio, the minimum reflux ratio. So from this graph is between the reflux ratio this and this axis and the cost. And the cost in dollar. It is in dollar. The first graph is about the fixed cost. The first one is the fixed cost. This is graph shows the fixed cost. This graph is for the fixed cost. Now what is the fixed cost? It is the cost of distillation column. The fixed cost is the cost of distillation column. It is the cost of distillation column. It is the cost of plates. So if we determine the cost of one plate and there are n number of plates in distillation column, then we will multiply the cost of one plate multiplied by the cost of number of. Suppose the cost of one plate is $10 and there are 10 plates, then we will multiply by 10. So the cost of distillation column will be $100. So this is the fixed cost is the cost of the column or the cost of the plates of distillation column. So as we from this figure, as the reflux ratio increases, the fixed cost ratio decreases. As the reflux ratio increases, the fixed cost decreases. This one, the fixed cost decreases as the reflux ratio increases. This means that as we increase the reflux ratio, the number of plates in the distillation column will decreases. So as we increases the reflux ratio, the number of plates in the distillation column will decreases, and hence the fixed cost or the cost of the plates will decreases. So as we increase the reflux ratio, the height of the distillation column will decrease, the number of plates in the distillation column will decrease, and the fixed cost of the column will decrease. So similarly, when we increase the reflux ratio, there is another type of graph which is the steam cost and the cooling water cost. Steam cost and the cooling water cost. So as we increase the reflux ratio, the height of the distillation column will decreases. This from this figure, or the fixed cost decreases, but the cost of the condenser and cost of the reboiler will increases. It is because when we increase the reflux ratios, we decrease, as we know that. So when we increase the reflux ratio, we are decreasing the height of distillation column. As we decrease the height of distillation column, there will be minimum number of plates in the distillation column. So in order to obtain product having required purity, in order to obtain the distillate and bottom product having specific concentration of a specific component, then we will use large condenser and large reboiler. So when we increase the reflux ratio, the height of the distillation column will decrease, the size of the distillation column will decrease, and as the size and height of the distillation column decreases, as the number of plates in the distillation column decreases, the fixed cost will decreases. But as we increase the reflux ratio, the the cost of the steam which are we using in the reboiler, and the cost of cooling water which we are using in the condenser. In the condenser we are using cooling water in order to cool the top product of the distillation column, and in this reboiler we are heating the bottom product in order to remove more volatile component from the bottom product. So we are using steam in the reboiler and we are using cooling water in the condenser. So this is the condenser, and suppose this is the bottom product B, and this is the reboiler. So this is the reboiler. So when we increase the reflux ratio, when we from this graph, from this graph, as we increase the reflux ratio, the cost of the steam which we are using in the reboiler will increase, and the cost of the cooling water which we are using in the distillate or which we are using in the condenser will increase. So when we increase the reflux ratio, the cost of steam which we are using in the reboiler will increase. Similarly, the cost of the cooling water which we are using in the condenser will also increase. So this will also increase. Now when we combine the fixed cost and the cost of the cooling water and steam, then we will get another curve which is called the curve number 3. It is obtained from curve number 1 and curve number 2. So this is nothing but curve number 3, and this curve is curve number 3. So this curve is curve number 3. This curve is curve number 3. This one, right on the top of blue line. This curve. This curve is curve number 3. This curve will be called the curve number 3. So this curve is obtained. This is curve number 3, and this curve number 3 is obtained from curve number 1 and curve number 3, and it shows the total cost which consists of the fixed cost and cost of the steam plus cost of the cooling water. So in order to when the reflux ratio is minimum, then the cost of the cooling water and the cost of the steam will be minimum. So when the reflux ratio is minimum, then the height of the column will be very large. There will be large number of plate in the distillation column. So at this reflux ratio is called the minimum reflux ratio. This reflux ratio is called the minimum reflux ratio. So at this minimum reflux ratio, the height of the column and the number of plate in the distillation column will be very high. So the fixed cost of the column will be very high at the minimum reflux ratio. So at this minimum reflux ratio, the fixed cost of the column is very high. So this is the fixed cost. The fixed cost of the column is very high. This is the fixed cost of the column. But the cost of the cooling water and the cost of the steam is small. So the cost of the cooling water and cost of the steam, the cost of steam and cost of the cooling water is small, because as the height of the column increases, then the condenser duty and the reboiler duty decreases. But when we decrease the height of the distillation column, then the condenser duty and the duty of the reboiler will increase. So at minimum reflux ratio, the condenser and reboiler duty is minimum, but the height of the column is high and there are many number of plates, so the fixed cost is large. So this is the fixed cost, and this shows the cost of the condenser and cooling water. So the cost of the cooling water and cost of the reboiler. So now when we increase the reflux ratio, then the fixed cost decreases, and the cost of the cooling water and the cost of the steam or the operating cost, this line is called operating cost. So when we increase the reflux ratio, the fixed cost decreases, but the operating cost or the cost of the cooling water and cost of the reboiler increases. So now this is the maximum reflux ratio. In this side, this is the maximum reflux ratio in this side, this direction. Now what will be the optimum reflux ratio? The optimum reflux ratio will be that reflux ratio on which the total cost will be minimum. So at this point, this is the combined curve, the fixed cost and the operating cost line. So fixed cost plus operating cost line will give us the total cost line. So what will be the minimum reflux ratio? What will be the optimum reflux ratio? The optimum reflux ratio will be that reflux ratio at which the total cost of the column will be minimum. So at which point of this curve the cost is minimum? So it is a simple question. At which point of this curve, this curve number C, at which point of this curve the cost is minimum? So at this point the cost of the column is minimum. So at this point the cost of the column is minimum. So this point, the point at which cost of the column is minimum. So the point at which the fixed and operating cost are minimum is called the optimum cost, and at this cost the reflux ratio which we obtained will be called the optimum reflux ratio. So this reflux ratio is called the optimum reflux ratio, is denoted by ROTP. So at this point the reflux ratio is called the optimum reflux ratio. So we should keep the reflux ratio at optimum value in order to obtain a purified product in the distillation column. So we should operate the distillation column at a optimum reflux ratio. So we should operate the distillation column at optimum reflux ratio. Now what will be the optimum reflux ratio? So there is a general relation that the optimum reflux ratio is there is a general relation that the optimum reflux ratio should so there is a general relation that the optimum reflux ratio, this is ROCT, optimum reflux ratio should be optimum reflux ratio ROCT, this is the optimum reflux ratio, is equal to 1.1 to 1.5 times the minimum reflux ratio. Minimum reflux ratio, MIN. So the optimum reflux ratio will be, equal to 1.1 times the minimum reflux ratio. It can be 1.2 times the minimum reflux ratio. So the general equation is that the optimum reflux ratio is equal to, it can be 1.2 times the minimum reflux ratio. It can be optimum reflux ratio 1.3 times the minimum reflux ratio. Similarly, the optimum reflux ratio can be 1.4 times the minimum reflux ratio. So it can be 1.5 times the minimum reflux ratio. 1.5 times ROPT means the optimum reflux ratio. So the optimum reflux ratio can be between 1.1 to 1.5 times the minimum reflux ratio. So this was all about the minimum reflux ratio, the optimum reflux ratio, and the distillation column. Thank you very much.